Thank you, Tajinder, and welcome to everybody to the third seminar in the current series. And it's a great pleasure for me to welcome my old friend Maurice De Gosson, who has taught me so much about symplectic geometry. I remember meeting him, totally unknown who he was, when he was sitting in the seminar I was giving, and he was nodding at everything I said. And I thought, wow, who is this guy who agrees with almost everything I'm saying? And we then talked. And then he invited me to, where was it now? Somewhere in Sweden.
Karlskrona.
That's right, Karlskrona. Such a strange place to be discussing symplectic geometry. But Maurice has written at least 4 books on symplectic geometry and quantum mechanics. And I found them all extremely interesting and always very sad that they are not well known in the physics community, because they were written for physicists in mind. They weren't these dry mathematical books that we physicists find so difficult to understand. He really bridges the gap between physics and mathematics in a brilliant way, in my view. Anyway, what he's going to talk about today is a very interesting idea of Gromov's, which is known as the no-squeezing theorem. And so he's taken, and that's where the symplectic camel comes from. So the symplectic camel, his title, the symplectic camel, quantum blobs, and the metatron, exploring the interplay of symplectic mechanics and quantum principles. Maurice, welcome.
Well, thank you very much, Basil, for your kind introduction. Actually, I'm trying to be a physicist, but I'm just a mathematician. But my book on symplectic geometry is more cited by more physicists than by mathematicians, actually. So I have partially succeeded anyway in my efforts. Okay, I'm going to give a more or less a survey talk with some new insights or some new ideas. I have the same eye problems Basil had a few weeks ago, so it's a little bit hard for me to read my own slides, so it will be perhaps a little bit bizarre, all this. And also my voice is not so good, so I might get very hoarse and you might be unable to understand what I say. Anyway, I'll do my best. So thank you very much and good afternoon, everybody here. So I'm going to start very softly by just recalling, by recalling Newton's second law, which is at the basis of everything, actually. Well, I mean, this is known by every first-year student. Of course, you can rephrase Newton's second law when you have a potential as the equation mx double dot equals to minus the partial derivative of the potential with respect to x by introducing a function called the Hamiltonian function. And when you do this, you see that Newton's second law is equivalent to the is equivalent to 2 equations which are called the Hamiltonian equations of classical mechanics. This is, of course, totally elementary, except that these 2 equations have far-reaching consequences, which I try to explain now. I'm sorry to begin in a very, very trivial way. Okay, hold on. Back here again, sorry for this. Good, yes. So Hamilton's equation can be generalized, of course, to arbitrary degrees of freedom. So you get systems of equations, of partial differential equations. They are written in collective manner as x dot t equals to the gradient of h and p, and so on and so on and so on. And this is the important point, they can be rewritten introducing the matrix J, which is called the standard symplectic matrix. It's a very, very simple matrix. Geometrically, it transforms a vector xp into the vector p minus x. Yeah. So it just flips the variables and adds a minus sign in front of the p here. They are typically forming a dynamical system. What is a dynamical system? Well, mathematically, a dynamical system is just a system of first-order partial differential equations with variable coefficients, if you want. My Hamiltonians are always time-dependent because it's worth the effort, and there's not very much to do to go from the time-independent case to the time-dependent case. I mean, it's just a matter of notations. Okay, so having rewritten Hamilton's equations as a dynamical system associated with a vector field xh called the Hamiltonian vector field, then we can define the flow. You know, if you have a dynamical system, you can always determine a flow. The flow is the time-dependent mapping, which takes a point at time t prime to another point at time later time t or previous time t here. And this flow I just denoted by ftt prime h superscript h to just so show from which Hamiltonian it comes here. And when you make these mappings act on points, phase-based points, you get so-called phase trajectories here. Good. So these mappings, flow mappings, have trivial properties. For instance, FTH TT prime. FTT prime times FT prime T double prime is equal to FT T double prime. It's a kind of semi-group property. Then FTT is the identity for each T, and you can invert it here. Now, often one makes things a little bit simpler by taking T prime equal to 0, in which case we write simply FTH here. Okay, then unless the Hamiltonian is time independent, we do not have the group property here, ft times ft prime equals to ft plus t prime here. So this is one of the minor inconveniences one has when one considers the time-dependent case. Now, actually, these flow mappings are quite flexible. You can do many things with them. For instance, if you take two flows, FTH and FTK, corresponding to two different Hamiltonians, H and T, you can multiply them. Of course, you can compose them. And in this case, you see that the product corresponds to a third Hamiltonian flow, the one associated with the Hamiltonian H delta K, where delta K, H delta K is given by the formula H ZT plus and so on and so on and so on. So the product of two Hamiltonian flows is a Hamiltonian flow. Similarly, we have other properties, but then the main one, which I will discuss a little bit further, is Liouville's theorem. Well, Liouville's theorem says that any Hamiltonian flow preserves phase-space volume. That is, if you take a subset omega, a measurable subset omega of phase space, and if you apply the flow to it, the volume will not change. This is called incompressibility. The proof is not very difficult to you find it everywhere in the literature. Well, one of the simplest and most rigorous sources is in Arnold's book, Mathematical Methods of Classical Physics, and so on. The idea is very simple. It's just that the divergence of the Hamiltonian flow is equal to 0. And it's known from the theory of dynamical systems that if you have a dynamical system with vector field with divergence 0, then it's automatically volume preserving. So beware, this property is not typical at all of Hamiltonian systems. People always make a little confusion and think that, okay, as soon as we have incompressibility, this means that you have a Hamiltonian flow. This is not true. Even our good friend Roger Penrose makes this little error, well, in his famous book, The Emperor's New Mind. I mean, well, that's a little bit of misunderstanding of the Hamiltonian character, because conservation of volume is not conservation of shape here. For instance, you have Katoch's theorem, which is quite subtle here, which says that if you have a very big phase-space subset and a smaller one, you can always, sorry, if you have two subsets of phase-space with similar volume, then you can always squeeze almost everything of the first one into the second one using Hamiltonian flow. More spectacularly is Booth's theorem, who proved that the property of n-transitivity, said that take a large number of points, n, for instance, at time t prime, and take another number of n points at a further time t, both sets of points having the same sign, then you can always construct a Hamiltonian function whose flows takes the first set to the second one. That is, no matter if the first n points are extremely concentrated around a point and the other points are extremely spread out, then you can always transform the first set into the second. Here is one of my ugly drawings. And as I told you, I'm not an artist. On the left side, you see a cloud of points enclosed in a small volume. On the right side, you see another cloud of points having roughly the shape of an S here, but it has the same volume, even if all the other points are much more spread out here. The proof of this is not very difficult, but it shows that, well, not only can you get huge sets after having applied a Hamiltonian flow, but these huge sets can be contained also in sets having arbitrarily small volume. You know, so this is now the thing is that actually, in addition to satisfying Lewin's theorem, Hamiltonian flows are symplectic, and let me explain that a little bit here. A crucial fact is that Hamiltonian flows consist of canonical transformations, as they are called in physics. Well, in mathematics, they are rather called symplectic transformations or symplectomorphisms. Okay, symplectomorphism is a little bit perhaps more, well, it sounds more mathematical, but it's exactly the same thing, symplectic transform here. You know, so the theorem is that let H be a Hamiltonian function, time dependent or not. Each diffeomorphism FTT prime H. Yeah, well, the flow mappings are all diffeomorphisms. That is, they are C1, they are at least once differentiable in all the variables. In fact, they are C infinite if you take a C infinite Hamiltonian functions. And diffeomorphism means that they are bijective and that their inverses are also smooth here. So each FTT prime H is a symplectomorphism of phase space. R2M sigma. What is sigma? Sigma is the symplectic structure, the standard symplectic structure here. Equivalent, this is perhaps a little bit more understandable for the non-expert. It means that at each point Z, the Jacobian matrix of FTT prime H bar, which I denote by STT prime Z here, is a symplectic matrix, which means that, well, the matrices S here satisfy a certain property, which is S transpose JS equal to SJ S transpose equal to J, where J is the standard symplectic matrix previously introduced. It's a very simple property. If you replace J by the identity, you would get STS equal to SST equal to the identity. That would define an orthogonal matrix, a rotation, for instance. Here you have the addition at J, which introduced a twist with respect as opposed to the identity matrix. But this is what makes the whole difference. Fine. Here, so the proof, well, I'll give you one proof here. It's elementary. You show by doing some calculations that the Jacobian matrices STT prime H satisfy the differential equation 1 here. Good. That STT is equal to the identity is anyway clear. So you saw this, where D squared H is the Hessian matrix of the diffeomorphism FTT prime H. Then you set AT equal to STT JST and makes a few calculations. You see that the derivative of this AT is equal to 0. Well, if it's equal to 0, it means that it's constant. And if it's constant, AT is equal to A0. Now, replace T by 0 in A0, well, then you get ST transpose JST, and it must be equal to J. Hence, ST must be a symplectic matrix. So this proof is simple because it's of an elementary nature. You can extend it to manifolds, but then you have to use so-called intrinsic calculus and the language of contraction operators and all that. It becomes much simpler, much more elegant. But to understand it, you need a certain background in differential geometry. So this is why I did do it here. Good. So this being said, now let's turn to the symplectic camel, having in mind that our flow mappings are symplectic. So more spectacular than Katok and Boothby's results are Misha Gromov's property of symplectic non-squeezing, which goes back to 1985. Now I used to write about it as a recent result. Now the years are gone; it's no longer that recent. He states the symplectic camel principle. Well, symplectic camel principle is actually a little different statement, but we won't care about that. Symplectic camel, why expect them? Because it's easier for a camel to go through the eye of a needle than for a rich man to enter into the kingdom of God. Here, in this case, the eye of the needle is a hole in a plane of conjugate coordinates, and the camel, well, it's a phase-based subset here. So we can state it in two ways. The first one is that we take the phase space and we choose any plane of conjugate coordinates xj, pj. That these variables are conjugated essentially here. With a circular hole with radius small r cut in this plane here. Now take a phase-space ball over this plane here with radius r and try to squeeze this ball through the hole here. Well, using the Hamiltonian flow. If the Hamiltonian flow consisted of arbitrary diffeomorphisms, volume-preserving diffeomorphisms, we could do it without any difficulty. We could just transform the phase-space set into a kind of sausage and pass it through the hole, no problem. But if these diffeomorphisms are symplectomorphisms, as is the case with Hamiltonian flows, you can only do it if the hole with radius r is larger than the size of the initial ball here. This is a phenomenon of symplectic rigidity, as it is called here. So there's no Hamiltonian function h whose flow can squeeze the ball through a hole with smaller radius here. An equivalent statement is, I'll discuss that in a moment, take a phase-space ball with radius r over the plane here and a Hamiltonian flow. Deform that ball with a Hamiltonian flow. Then the orthogonal projection of this image will never decrease under pi r squared. And this is reminiscent of the uncertainty principle. And this is the whole point here. I have tried to, dynamical interpretation. Yeah, well, this is actually a direct consequence of what I just said. Suppose we have a cloud of points in phase space with projection on any of the conjugated planes with area pi r squared. Well, deform this cloud using a Hamiltonian flow. Then see that conservation of volume has nothing to do with conservation of size here. Actually, due to Gromov theorem, the initial cloud will distort while keeping orthogonal projection with area at least the initial pi r squared. So this is very close in spirit to the uncertainty principle, where you can't reduce something here, the size of a cloud, the area of a cloud, to something smaller. A new result says actually that you can even do the same kind of argument if you replace the plane of conjugate variables by a space of conjugate variables. For instance, x1, p1, x2, p2, x3, p3. This was recently proved by Abbordandolo, an Italian mathematician here, but it only works in the case which is of interest to us, by the way. It only works if your symplectomorphisms are linear, that is, if they come from a quadratic Hamiltonian. There are counterexamples otherwise. And this result is interesting when you deal with reduced quantum systems, with reduced phase space. Well, okay, I won't discuss this too much here. So, okay, this is a rather recent picture of Mikhail Gromov. He looks like a mathematician, for sure. Here, he's originally Russian. He was, during his younger years, he was a circus artist here, and then he became French, and he got in 2009, he got the Abel Prize, which is the equivalent of the Nobel Prize for mathematics. You know, many people believe that or talk about the Fields Medal as the equivalent of the Nobel Prize. It's not true, because you must be under 40 to get the Fields Medal. So the Abel Prize is really the equivalent of the Nobel Prize in mathematics. By the way, it's another French mathematician, Michel Talleyrand, who got yesterday the Nobel Prize in mathematics. He comes from probability theory. Okay, so Hollow movement. Hey, let's talk a little bit about philosophy here. But the Bohm and Hiley Hollow movement refers to ontological, now to the concept developed by the physicist David Bohm and his collaborator, close collaborator, Hiley. Okay, blah, blah, blah. I have written a few things I had in mind here. Okay, of course, I cite the work of Bohm and of Hiley here. So the Hollow movement is a dynamic process that underlies both the physical and fundamental and mental aspects of existence. Well, this is here in philosophy. Okay, here. And I find the concept beautiful. And actually, Basil and myself wrote a paper about that a few years ago here. Oh, it was 10 years ago, in the journal Mind and Matter. Discussing a little bit that the whole movement, the Hamiltonian flows, it's like a symphony. Of course, this is not mathematical; it's rather physical. But then don't forget also that Richard Feynman said that philosophy of science is about as useful to scientists as ornithology and art is to birds. Well, of course, this was certainly a provocative statement. Sorry, Basil, for that, but I like this citation. I'm not talking about serious epistemologists and ontologists and serious philosophers, of course. No, not those who discuss whether the sun dreams or not and things like that, and Mike told me here. But I mean, I think I'm not a philosopher. That is much more versed into these things as I am. But I find it, well, yes, poetry is always useful. Good. So now quantum blobs. Yeah, well, quantum blobs, I, so to say, invented the notion of quantum blob. The name seems a little bit ridiculous. I agree. I think that some people laughed at it. Okay, Basil, Basil was amused, so I decided to call it that way. So let us denote by B2N Z naught R, a phase space ball centered at a point Z naught and with radius R. And it's okay, it's defined in a quite simple way. So definition, a quantum blob in our symplectic phase space is just the image of such a ball by a linear symplectic transformation S. That's all. It's very simple. But what's the point of that definition? The point is that we can apply Gromov's theorem to these quantum blobs. And we see that the projection of a quantum blob on any plane of conjugate coordinates will always have an area at least pi r squared. So we are in the symplectic, in the uncertainty principle here in this case. Yes, because the symplectic ball here has the square root of h bar as a range, and this is the important thing here. So quantum blobs are the small phase space units compatible with the uncertainty principle of quantum mechanics. We'll see why here. Okay, they are distinguished from the usual quantum cells because they are much more flexible than these cubic quantum cells. Because if you apply a symplectic mapping to a quantum cell, you get something which is strange, whereas you get an ellipsoid if you do that with a quantum blob. Okay, first results were published in Foundation of Physics here, and yeah, okay. Well, it was introduced in 2003, blah 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 blah, and so on. Yes, well, that's about the same here, so it's uninteresting here. Okay, the first remarkable geometric property of the quantum blob is the one I just mentioned here. QB stands for quantum blob one. It's not such a good notation here, which follows from the symplectic camel principle. That's more or less what I told you a moment ago. Okay. Well, this is some self-advertising here. Cloud will distort. Yeah, well, okay. That's just repeating what I said a moment ago. Yeah. Good. So, yeah, okay. This is not just some self-advertising, but the New Scientist published a short paper on this, on my introduction of quantum blobs and the use of the symplectic camel in the uncertainty principle. So the author Reich actually wrote a few nice things here, but she missed a little bit the point here. These statements are very kind, but they miss the point because we have much more in this. It's not just, as she says, to replace, to use a theorem of symplectic geometry to make a statement which is equivalent to the uncertainty principle, which it is. It actually has many more implications, which I shall try to just discuss right now. Actually, yes, the first one, which is rather nice, is that if we take an arbitrary quantum state, rho hat, it's a mixed quantum state, we can define under certain conditions its covariance matrix here. Okay, it can be defined in a concise way with formula number 2. It's just a matrix where you have the variances, the covariances, and so on listed here. Okay, it's a covariance matrix here, in this case with the stochastic variable positions and momenta here. A well-known characterization, it's a famous one, but it's not known by all physicists, is that if you have a quantum state, if this is the covariance matrix of a quantum state and not just of an ordinary probability distribution, then the matrix sigma plus IH bar over 2J must be positive semi-definite. The proof of that is not simple. It was proved first, I think, by some Indian guys, Dutta and Mukunda, and put on a serious mathematical setting by Narkowicz, an American mathematician, in an already old paper, 1990, which has had a big impact on mathematics and the study of positive operators here. So this condition, sigma plus IH bar over 2J, semi-definite positive, is actually equivalent to the uncertainty principle. It is strong Robertson, Schrödinger form. Robertson, Schrödinger, and Kenner form, actually. And there's a lot of literature on that here. What I proved is that actually this condition is equivalent by saying that the covariance ellipsoid contains a quantum blob. You see, you have the covariance matrix. Using that, you can define the covariance ellipsoid. Oh, there's a typo here in the statement of the theorem. The ellipsoid should not be 1/2 of zt sigma z, but sigma minus 1 must be the inverse. That is actually the condition sigma plus I h bar over 2j positive implies that sigma is positive, definite, and hence invertible. So the sigma here should be replaced with sigma minus 1. Okay, the proof is I refuse to. It's very detailed in my physics report paper with Franz Rueff from 2009 here, where I studied these things rigorously from a mathematical point of view. So imagine here, it means that we have replaced an algebraic and analytic condition for mixed state by a purely geometric condition, which is a simple one. You have a phase-space ellipsoid, which represents the covariances. Well, if we are dealing with a quantum state, then this ellipsoid must contain a quantum blob. So this is, I think, the central point with these things here. Now, okay, now let's turn over to Gaussian quantum states, because we're going to see that actually Gaussian quantum states are analytical representations of quantum blobs. Well, I'm dealing with the most general quantum Gaussian state possible here. It's psi xy, formula 3 here. We have a normalizing constant here, and then we have the exponential here. Observe that we have 1 over 2h bar here, and then x plus y x. Oh, that's a small typo because it should be x plus y brackets and x dot x here, where x and y are real symmetric matrices. For example, if we take x equal to the identity and z naught equal to 0 and y equal to 0, then we get the standard coherent state, the standard Gaussian phi naught of x here, which is known to everybody. It's the simplest one, really. When you only take y equal to 0 here and an arbitrary x, then you get the generalized squeezed coherent state that they are called here. For instance, by choosing x diagonal or equal to scalar, you get the function phi x listed here as equation 5, which is really the standard coherent. You see, these states have all the property that they saturate the Robertson-Schrödinger inequality. That is, they saturate the uncertainty principle. They saturate the states of the type 4 or 5, saturate the Heisenberg uncertainty principle. The others, if you take y different from 0, they saturate the more general Robertson-Schrödinger uncertainty principle here. Exactly as quantum blobs saturate the uncertainty principle. So, actually, we're going to see the relationship between both here. Okay. You know, the Wigner transform, quick a few words. The Wigner transform is defined by the formula you see there. It's used as a quasi-probability distribution, because if psi is norm to 1 in L2, then the integral of W psi of the Wigner transform is equal to 1, and you have the marginal properties there here, which are valid if you have psi in L1 and L2. Now, if A is a classical observable and A hat its Weyl quantization, then the average value of A is obtained by the formula you see there. It's actually the classical observable weighted by the Wigner transform. So the Wigner transform really plays the role of a probability distribution. Here, a few words here. The datum of the Wigner transform of a state is equivalent to the datum of the state itself. I wanted to put that as a remark because it's not universally accepted. I have talked with some physicists who say, no, well, the Wigner transform, you forget about the phases and things like that. No, it's not true because of the equivalence you see there. So phase-based quantum mechanics is quantum mechanics usually. Yeah. Now, Wigner transform of Gaussians. I take these Gaussians here, psi x, y, and I take the Wigner transform. Turns out that the Wigner transform is extremely simple. We have just a normalizing factor pi h bar minus n here, and then an exponential. An exponential here, phase-based exponential with a matrix G. And this matrix G is symplectic. It's actually positive definite, and it's the product of ST and S, where S is given. It's a almost diagonal matrix, which has a very simple form here. And this is really a spectacular fact. It was proven by a mathematician called Janssen a long time ago, and then a new proof was given by Robert Littlejohn. This at Berkeley, but many years ago as well here. So why is this interesting? It's interesting because it allows us to identify the quantum blobs with the Gaussians in a very simple way. Look at the theorem. I define a mapping phi. It takes a quantum blob, SB to N and so on. To this quantum blob, we associate SST, and to this SST equal to G, we associate the Wigner transform of psi xy as defined in the previous page, and you get this here. And this is really a bijection. It's a bijection because this mapping does not depend on the choice of S defining the quantum blob. Because, of course, if you have SB to N, you could as well have S prime B to N for some other symplectic matrix X prime. But as I mentioned in the proof here, it doesn't matter. Because if we have SB to N and S prime B to N, then SST must be equal to S prime T. Yeah. Because you can say that, well, a symplectic transformation takes a ball into a quantum blob up to a rotation, up to a symplectic rotation, and a symplectic rotation does not change a ball. Yeah, well, actually, the proof actually works here for set naught equal to 0. Sorry, there's a typo. But then once you've done that for that naught equal to 0, it immediately generalizes to the right. So actually, this shows that Gaussians and quantum blobs are the same thing here. Good, yeah. Now, the new stuff. I mean, all this, what I have told you, has been known for some time already. I recently introduced the notion of polar duality. No, I did not introduce it. I used it because polar duality is something which exists, been existing for a long time already here. So I take a convex body. A convex body means that it has a non-empty interior and it's convex here in the Euclidean space Rnx, that is in configuration space here. By definition, its polar dual is the set X H bar of all P belonging to the dual of Rn, which I identify with momentum space then, such that the scalar product of Px is smaller or equal to H bar. Here, H bar is a positive constant one. That's how I begin mathematical papers when I talk about that, where H bar is a positive constant, usually taken to be one in the standard literature on convex geometry and equal to Planck's constant divided by 2 pi infinity. No, of course. And you'd have to really write that unit. Okay, so polar duality can be written as you see there in the formula there. P is in X H bar if and only if the scalar product of Px is smaller or equal to H bar for all X belonging to X here. It's easy to see that polar duality is reflexive. That is, that if you take twice the polar duality. You're back to the same set here. And anti-monotone, that is that if X is a subset of Y, then YH is a subset of XY. Also here, ellipsoids play a very important role in what we are doing here. So if I define an ellipsoid by AX smaller or equal to H bar, then its polar dual is defined by A minus 1, the inverse of A, XX smaller or equal to H bar. So polar duality acts by inverting the matrix of an ellipsoid here. So in particular, if you take the polar dual of the ball Bnx with square root of H bar as radius here, that's a ball in configuration space, you get the same, so to say, ball in momentum space here. And vice versa, of course, also here. And this means that, in a sense, polar duality acts as fixing balls in configuration space and momentum space. And actually, the fundamental property of this here, and its relation with quantum blobs, is the following here. Okay, these are rather recent results here, which I have written in a little bit different ways, following the needs of the people here. If you take an ellipsoid in configuration space Rnx, I should have said here a centered ellipsoid. You can do more than by translating it here. And XH bar is polar dual. The largest phase space ellipsoid contained in the product X times XH bar is a quantum. The largest phase space ellipsoid contained in a convex set is called the John ellipsoid in the mathematical literature. It is unique. Given an arbitrary convex set in an Euclidean space, it contains a unique ellipsoid with maximal volume contained into it, the John ellipsoid. It also contains a unique one containing that, and that's called the Löwner ellipsoid in convex geometry. And this property is very important, actually, here. Why? Understand immediately why. Proof, I've given here the sketch of a proof here. The idea is that you reduce, actually, the case of the product X times XH bar to the case where X is a ball with radius H bar, in which case X times XH bar is, as we saw on the previous slide, just the product of two balls, a configuration space ball with radius H bar and a momentum space radius bar. And the John ellipsoid of such a product is the phase space ball B2n square root of H bar. That is, it is just the elementary quantum blob here. Of course, then you can deform in the general case when you have an ellipsoid X. In the general case, you can just manipulate that, use the properties of the polar dual, and see that you get the quantum blob here. This is essential because it means, what does it mean? It means that if you choose an ellipsoid in configuration space, in everyday space here, just, I don't know, anything, then automatically to this, you can associate a quantum blobs that is an object of phase space. That is a Gaussian, since quantum blobs and Gaussians are the same thing here. And this is very much reminiscent of Pointillisme à la Signac. Pointillisme was a French painter who painted by representing his motives by dots, small paint dots here. Here, this is part of one, it's called, I think, the fisherman or something like that. You see, everything in configuration space is represented by dots here. That is, every point you see on this painting has a quantum blob associated with it. That is a Gaussian, a coherent state here. Yeah. This is why in one of the papers in Foundation of Physics, I talked about Pointillisme à la Signac, because I think it illustrates very well things. Now, there are many problems that arise here, and about which I will not be able to talk. But see, on this slide here, I show you, take the ball be an x with radius square root of h bar. You make correspond the product of the ball and its polar dual. Then to this you associated the John ellipsoid, to which we can associate the standard coherent state here. More generally, if you take an arbitrary ellipsoid, you do the same thing and you end up with a squeeze state here. Squeeze state. Now you might ask, yes, but okay, that's very nice, but why don't you obtain the other Gaussians? The Gaussians with y different from 0. Actually, you can do it. But to do that, instead of taking the polar dual in the momentum space, you must take it on what is called a Lagrangian plane in symplectic geometry. Lagrangian planes are actually the images by a symplectic transformation of either the x space or the p space. That is, you rotate them in a certain way, then you get planes of mixed coordinates, like, for instance, x1, x1p, x1p1, or x1, x2. You end up with mixtures of position coordinates and momentum coordinates. So you can obtain them all. But the most natural way is just to take the momentum space, so you obtain the squeeze coherent state. But you can obtain all of them here. Good. Okay, so now, let's go to something else, which is very closely related, Schrödinger's equation and quantization. Well, you know that Schrödinger, of course, that's the whole story. Everybody knows that. Postulated an equation. People were marvelous, saying yes. Well, how did he do that actually? But Schrödinger was not stupid. He knew what the Hamilton-Jacobi equation is. So it was not just an act of faith or an act of God that made him discover that. And actually, Schrödinger, without knowing it, had discovered the metaplectic group. I'm going to explain why here. But, however, as soon as we see Schrödinger's equation, we must ask ourselves, the H hat we have, the quantization of the classical Hamiltonian. What is it? How should we do it? We have basically two choices. We have Weil quantization, which I am using because it's neat and easy actually to handle thanks to the symplectic covariance properties. And then you have Born-Jordan quantization, which might very well be the correct one. By the way, just to answer a question to Basil, in Born-Jordan quantization, you don't have any collapse of wave functions and things like that, because Born-Jordan quantization is an algebraic one. You see, Born and Jordan introduced the matrix calculus, which was called often this time Hexen mathematics, which mathematics, because people were not familiar with matrices. And Heisenberg then joined them to write also a paper about that. I'm not going to go into really with all the details about that Born-Jordan quantization. I have the impression, it might be subjective, but I'm going to give some explanation of why it might be the correct approach to quantum mechanics, unfortunately. You see, it all arises from the ordering problem. Let's consider monomials of the type xjm, pjl. Weil quantization quantizes such a polynomial in the way you see there in the first line here. That is, you see, you have 1 over 2 up to 2L, and then you have a sum involving the binomial coefficients. It's very nice. So you have a peak in the middle, privileging, in a sense, the most equilibrium. In Born-Jordan quantization, all the quantizations are placed on the same footing, and then you take an average by dividing by L plus 1 here. In both cases, you can do the calculations, we get the same thing for the project SJPJ. Okay, I have detailed all these things very much in a I was going to say a recent book, but it's no longer that recent here. Now, the Springer book, and there's also a series of papers. But and it's funny, these papers have been well received by the mathematical community, especially people working in time frequency analysis, and less in physics. The point is, why do people in time frequency analysis like Born-Jordan quantization? Because it has a tendency to erase the interference effects in the Wigner formulation. And in time frequency analysis, it's not like in quantum mechanics, these interference effects are often unwanted. So one has the impression, and it's a vague one, that Born-Jordan makes things neater here. However, here, both quantizations coincide for all quadratic Hamiltonians, generalized harmonic oscillator, and for all physical Hamiltonians. That is, Hamiltonians of the type which you have here. It's not only a Hamiltonian with a vector field. You can also describe the Coriolis forces and things like that. But Sturio was a great specialist of symplectic geometry, called these Maxwell Hamiltonians. They are actually the only who are covariant under the action of the Galilean group anyway. So you cannot distinguish Weil from Born-Jordan here for Hamiltonians of this type. This is, I think, why people are not so interested in considering one Born-Jordan instead of Weil. However, there are physical cases where both quantizations do not coincide. For instance, in a paper, when did I do that here? Oh, yeah, that's the, oh, yes. Oh, 2017, yes. I took up what is called, you can find that on Wikipedia, it's discussed, the angular momentum dilemma. Yeah. The square of the angular momentum gives you two different results if you use first Weil and then Born-Jordan quantization. And it seems that it's Born-Jordan quantization which gives the correct answer. You can see that. Yeah? And also in a more recent paper with a bunch of guys from Gaussian, from the Quantum Optics Institute near Munich here, it's just been put online here, where we also discussed, it's a long paper, where we also discussed the benefits of using Born-Jordan, and they are actually performing experiments, physical experiments, to see whether all this can be true or not. So still, Born-Jordan quantization is more complicated in the general case, but it's very appealing. Okay, so Schrödinger equation. Yeah. Yes, a little bit blah blah blah. Just telling a little bit the story of what I have done. Let's go perhaps to the point here. Okay, yeah. There are two ways for me to justify the Schrödinger's equation. First, the one I'm going to explain the next slide here, and actually it's in the book with forward by Basil Heidi. This method is not new, and actually I did not really invent it, because you can find it in harmonic analysis books and even in disguised forming device books. I exposed this at Rutgers University in the US a long time ago when I was visiting Yale. Our friend Shelley Goldstein invited me to come and give a talk in the math department. And I exposed the method I'm going to show you. It was a scandal. It was just like preaching for atheism in the Vatican. I mean, this is not possible. You cannot deduce. It's impossible to deduce Schrödinger's equation from classical arguments. No, they were wrong, of course. But I've often noticed such strong reactions from our friends, physicists. Yeah. There's another way, which unfortunately I will not have time to expose, which Glenn Dennis, Basil, and myself wrote in a recent paper. Yeah, this one is rather recent. On Bohm's quantum potential as internal energy. There we show, in this method, we actually show that following an old idea of Enrico Fermi, that to every particle you can associate a phase space by just rewriting the certain equation and performing a Gaussian transformation. This phase space set contains a quantum blob, so this we are very happy. And in addition, it makes appear the quantum potential here. Then by adding this quantum potential to the classical Hamiltonian, you automatically get the modular equations and you get Schrödinger's equation. This is perhaps a more physical way to do things, but I don't have time to really discuss this yet. So what did I do a long time ago? To introduce the metaplectron. I call that the metatron, but Mike suggests the metaplectron. It sounds better because it comes from the metaplectic group. There you start just with a quadratic Hamiltonian. You get the phase space flow, which consists of symplectic matrices. That's very fine. So you get a curve in the symplectic group, of course. Yeah. The flow consists of symplectic matrices ST, such that S naught is equal to the identity. You let T vary, you get a curve, and then we apply what is called the principle of monodromy. You see, the symplectic group is a classical group, as people say. It's connected, has many nice topological properties, and in particular, it has covering groups of all orders. You have a stack of covering groups. One of these covering groups, the order 2 covering groups, the double covering SPN, can be realized and fabricated as a group of unitary operators. And this group of unitary operators is called the metaplectic group. Now, the principle of monodromy says that if you have a curve in a group, in a D group, then you can lift that curve to any of its covering groups. So we lift it to the metaplectic group. In addition, we can choose this lift so it goes through the identity of the metaplectic group. Here is normally a picture. Yeah, it's a very ugly one, I agree. The ellipse that at the bottom is SPN, the symplectic group. There you see in red is the curve of symplectic matrices, which represents the flow of the Hamiltonian. And the upper ellipse, you see two red curves. The one is dotted, you see, because MPN, the metaplectic group, is a double cover of SPN. So, of course, if you lift the curve from SPN to MPN, you will get two curves. But one of them can be chosen to be that one going through the identity of MPN or any other group of elements here. So let's focus on the one, on the red one here, which goes through the identity. We have, since MPN consists of unitary operators, we get a curve ST hat of unitary operators. Good, fine. What happens next? Well. It turns out, and this is an important fact, if you have a covering, actually, you can choose the covering mapping in infinitely many ways. That is, if you have pi, one covering mapping, then you can replace it by A minus 1 by A, where A is any inner automorphism of the covering group here. So you have choices, you have multiple choices. What we do is to choose the choice here. Okay, the J hat epsilon is the Fourier transform up just to I. And here I can choose. And this J hat epsilon belongs to MPN always here, Fourier transform. But for any choice of epsilon, what I do here is to choose epsilon equal to H bar. Why? Because the curve then of operators ST hat will correspond to the real quantum evolution in the sense that ST hat psi 0 will represent, if we follow Max Born, will represent a probability amplitude. And this choice epsilon equal to H bar is the only one which leads to this choice here. Okay, the argument is in fact a little bit longer, but I do not have time to develop it. But as you see, then what happens is that we get in all cases, for any choice of epsilon, we will have Schrödinger's equation. And the Schrödinger equation, the right one, that is with epsilon equal to h bar, is obtained by accepting Max Born's suggestion that the wave function, that is the solution xt, is the probability amplitude. Actually, I'm oversimplifying because you can do it another way as well, by directly relating that to quantum blobs, by saying, yes, okay, we have a curve of metaplectic operators coming from a quadratic Hamiltonian, and this will transform a coherent state into a squeezed coherent state. That is, will transform a quantum blob into a quantum blob, which imposes a posteriori then the chose epsilon equal to h bar. I'm sorry, but it will have taken us a little bit too long here. Okay. Okay, the general case. Okay, we've been dealing with quadratic Hamiltonians, but yeah, but how do we do it with arbitrary Hamiltonians, Maxwell Hamiltonians? Well, the idea is the same. You cut the time interval t prime into smaller intervals, right, by introducing large n points, large n times, and this large n will let it go to infinity. Then on each small interval, for instance, T1, T2, T2, T3, we approximate the flow FTH by linearizing it. Linearizing it means that we replace it by the compose of a linear symplectomorphism, that is a symplectic matrix, and a translation. Then you do your little job by finding the equation which is satisfied by all that, and you let n tend to infinity. It's technical, it takes a few pages of calculation, but it works. And you see that once again, the operator ut t prime hat defined here as a limit satisfies Schrödinger equation. It's a kind of Feynman integral reconstruction after all. Okay. There are other methods for doing that. For instance, in our paper with Basil, we have used short-time quantum propagators and Bohmian trajectories. Then, in a more recent paper with Cohen and Heine, we have studied the quantum Zeno effect from the same perspective. It was published in Annals of Physics. Yes. Okay. Not so. Oh yeah, only 8 years ago. That's quite fresh. Okay. Yeah, and okay. I didn't make quite clear here the relation between quantum blobs and the Schrödinger picture because of lack of time and lack of competence, perhaps here, but it's there. So thank you very much for your polite and kind attention. That was it.
Thank you. Thank you for a very beautiful lecture. Really amazing. Basil, would you like to continue the session, or would you like me to do it?
Oh, well, would you take over, please? Because I'm a little bit too close to it.
Okay, great. Thank you. So the talk is open for questions. Very welcome to ask questions, please.
I have a question, Michael Berry, if you can hear me. Can you hear me?
Yeah, please go ahead. Please go ahead.
Yes. Maurice, thank you. Nice to see you again after a long time.
Same here. Nice to see you too.
Yes. Now, my question is this. This beautiful theorem of Gromov is to do with sharply defined blobs. Now, what you're doing in quantum mechanics is slightly different because your blobs are Gaussian, and you know, of course, very clearly that if you would define a Wigner function which was sharply defined, you get into all kinds of problems with exponential sudden explosion. Yes. So I accept the classical version of the Gromov, the classical version where you have smoothed out blobs instead of sharply defined blob. Okay. Yes. Now, as you've explained, it tells you something rather deep and beautiful about the evolution of classical states. Now, you know that if you take a corresponding quantum state, it needn't be a Gaussian, but let it be, and you evolve this quantum mechanically in some potential, then it can be very different. It will get complicated in the way that the classical one does, but after some time it will get differently complicated. So my question is, for this quantum case, you look for a long time and your Wigner function is spread out into some interesting, complicated way. What does the Gromov theorem in your quantum version tell you about the quantum state, other than the very general statement of the uncertainty principle, which...
Yes, okay, but this is the perfect question, because you're right. This is the difficult part. You see, actually, you can generalize the notion of quantum blob by saying that the image of a ball by an arbitrary symplectomorphism. And of course, this allows you to consider arbitrary flows and arbitrary Hamiltonians. The problem is that it's not obvious at all how what kind of function you should associate with such a ball deformed by an arbitrary symplectomorphism. What I have in mind, and this is why I'm interested in polar duality, is that this could be the key here, because polar duality for convex sets allows you to manipulate general convex set and to make correspond to them quite complicated functions. See, have you heard about the Santalo point, for instance? The Santalo point is what should replace the center of a convex set when it's no longer an ellipsoid. And you have quite a theory with which I'm not yet quite familiar about how to associate to these convex sets, to these convex sets functions. It has to do with the so-called Minkowski functional, and it's an extremely rich theory, and I'm learning it now. And I think that might be the key. Otherwise, in the general case, as you mentioned, the only thing I can do are approximations. WKB or semi-classical approximations. But it seems to me that it doesn't lead very, very far.
You see, I'm tempted to think that there is something corresponding to this Gromov theorem in detail. And I have another analogy. You see, in the early days of quantum chaos, we were interested in not in evolution of states, but in stationary states, eigenstates, of systems which are classically chaotic. And it turned out that the distribution of the eigenvalues, the energy levels, at least in some ranges, is very well modeled by random matrix theory. And the question was why? And what I found was that this universality, independent of the particular quantum system, so long as it was classically chaotic, had its origin in a classical universality to do with the distribution of very long periodic orbits on the energy surface. It was a kind of classical phase-space democracy underlies quantum mechanics this beautiful property. Now, you have described with the Gromov theorem a beautiful classical universality. And so I would not be surprised if there were a well-defined, detailed quantum universality. You see, going back now to evolution, in the early days, we had the idea that if you had a Gaussian blob or some other kind of blob, but well-defined, for example, associated with a classical energy surface or invariant curve, it would evolve into something complicated under some mapping, but the quantum would cease to follow the classical, where the filaments of the blob became, in a not well-defined sense, smaller than Planck's constant. And we showed that this was true. It did numerical calculations, and you indeed see that in a chaotic classical system, the quantum stops following the classical when it gets too complicated. Now, this really smells of the Gromov theorem somehow, but I don't know how. And this is my question. What detailed...
Okay, there are people working on the case where you have very small subsets in phase space, which I'm not familiar with these things yet, hopefully, but I know that exists. Yes, there's a question of scale and of size. So this might be related to what you are telling me.
Yes. Okay.
As a sub-Planckian state, that's actually what you mean here.
Yes. And by the way, just a side remark, I was very pleased to see you refer to the Robertson-Schrödinger version of the uncertainty principle, because this doesn't have the reputation and widespread acceptance it deserves to have, because it's much more general than that. And for example, as Schrödinger points out, if you have a Gaussian wave packet in free space which spreads, according to the Heisenberg version, the system which starts out with minimum uncertainty will soon have a greater uncertainty. But with the Schrödinger version, it's always minimum uncertainty. So it's much stronger. I've used this myself in various other contexts. So I was very pleased that you mentioned that, because it's obvious. Because the Gromov theorem the Gromov theorem, of course, is always true, however long you evolve a system for. And so it's very natural that you should use.
Exactly. And what people do not notice is that if you transform the Heisenberg inequality, saturated using a symplectic transformation, you do not longer get Heisenberg. You get Robertson Schrödinger. It makes covariance appear. Yes. That's why it's fundamental.
Yes. Thank you. Thank you very much.
Thank you, Michael.
Thank you. Christy, go ahead, please.
Hello, can you hear me?
Yes, I can hear.
All right.
I cannot see you, but
I was very happy to see your talk, and I have a few questions. So I will ask them. If there are no other questions, I will ask one right now. If I understand well, you said that the Born-Jordan quantization doesn't need the wave function collapse?
Well, because there's no wave function in the Born-Jordan.
Okay.
It's just between operators. But the expert is Basil. He has discussed that in many, because he does not like the collapse either. I don't know what to think. I'm not a physicist, unfortunately. But no, you collapse nothing actually. It's an algebra of operator. Matrices, as they were called in the old time. It's very appealing. It can be justified mathematically, and well, that's all what I have to.
Just related to that, Maurice, let's say when we make a quantum measurement, let's not talk of collapse, but there are probabilities for different outcomes.
Yeah.
How do I see that in the matrix, in the operator algebra picture, in your picture?
I don't know what to answer, but observe that in my derivation, so to say, of Schrödinger's equation, it's either Born-Jordan or Weil, but both are equivalent in these cases here.
Okay.
So I don't know exactly how to answer your question.
Okay, no problem. I have a related question. Is the Jordan von Neumann-Wigner formulation, the 1939 paper, also known as Jordan's algebraic formulation, that is different from what you call Born-Jordan?
I think so, because Born-Jordan actually was, I think, in 23 and 24, a couple of years before Weil, actually.
Okay.
Then Weil won, so to say, because, of course, his quantization looks simpler.
Okay.
But I'm not, well, this is a very interesting question. I've written papers where I have discussed this problem. And in some branches of science, like time frequency analysis of signal theory, they prefer Born-Jordan.
Okay.
The people working on that. For instance, I've been working with a guy we have published yet, Cohen, Leon Cohen, who has created so-called Cohen classes, and of which Weil and Born-Jordan are particular cases. And it seems that for all practical purposes, in the acoustic, signal theory, and so on, Born-Jordan works better or gives better results. It does not mean, of course, automatically that it's better for quantum mechanics. I don't know. My expertise stops at this point.
Thank you. So just another related question. for the quantum to classical transition. So we loosely speak of classical mechanics as the h bar going to zero limit of quantum mechanics. Can I somehow think of, in your picture in phase space, the fundamental ball having a radius square root h bar, which is dynamically shrinking to zero as you go from the quantum to classical limit?
Well, in the limit h going to zero, the quantum blobs become points, you see? So
yeah, but I want to see that happen continuously, not in a discontinuous sense.
The limit is very singular. The limit is very singular.
The limit being singular seems to suggest perhaps there's a theory more general than both quantum and classical mechanics where, you know, the root h bar continuously goes to zero.
I wouldn't be surprised, but I mean, you see, if you take the analogy between quantum blobs and coherent states, a quantum blob goes to a point, yes, but the corresponding coherent states are all of them also go to a Dirac function. So it's really not nice. I mean, you lose enormously information by doing this. That's how I see it.
Okay. Yeah, thank you. Bernd, please go ahead.
Because one thing, letting h go to zero must be very difficult. H is a constant of nature, which has been fixed yet and all that. So to let h go to zero means that you rescale other variables.
No, I agree. I was just thinking, could I make h a function of the number of degrees of freedom in a macroscopic system as f of h bar goes to something dimensionally the same, but yeah, it's okay. Thank you. I get your point. Bernd, please go ahead.
Okay, so just as usual to clear up a little bit of history. So the Born-Jordan paper was in 1925, and at this or not. So you can of course also correct me if you think I'm. So the first paper by Jordan was in 1924, and there were also a few papers by Heisenberg and Born in 1924. But the famous paper on quantum mechanics, which was the title, was in 1925. And the original idea why they used matrices was because Born was thinking that nature really makes jumps, so that it's basically discrete. And the trouble with the measurement problem in quantum mechanics comes if you reintroduce the continuum, because then you have smooth transitions and smooth time evolutions, and you cannot explain why we get sharp eigenvalues and why don't we get a continuum of values. And in the original formulation of Born and Jordan, of course, they didn't use wave functions in 1925. It was too early. They really used the kind of discrete mathematics also.
Yes, absolutely, yeah. That's right.
And when the trouble with the measurement problem started when Schrödinger reintroduced the continuum, so smooth wave functions and differential operators and all this stuff. And later von Neumann showed that both views are equivalent, and then because differential equations are more familiar and the continuum is more familiar, people got used to this continuum picture, and then they were left with the measurement problem. And to add something on to Jinder's question concerning the Jordan-Wigner-von Neumann formulation, actually Jordan started his work with Jordan algebras as a kind of axiomatization of matrix mechanics. So he tried to crystallize out what's the most, economic way to describe expectation values and to describe observables. And he noticed that, for example, the product of two Hermitian matrices is no longer a Hermitian matrix if they do not commute.
I was not aware of these facts. Thank you for bringing them to my attention.
And the so-called Jordan product or symmetric product was found by Jordan because he wanted to define an algebra of observables so that the product of two Hermitian matrices is again a Hermitian matrix. And then he found his Jordan algebras, and then he was for a time quite optimistic and said, okay, then I can look at the properties of Jordan algebras, and maybe we are lucky and there are more Jordan algebras than the Jordan algebras we get from, looking at the Hermitian observables of quantum mechanics. And this was the initial hope of Jordan and, of course, von Neumann and Wigner. And then there's also the so-called Jordan formulation of quantum mechanics, where you only work with Hermitian operators. You also describe the states then by Hermitian idempotence. So sorry, this was a little bit of trouble with language. So Jordan described in the states not by wave functions, but by Hermitian operators which square to themselves, so idempotence. And they should describe so the primitive idempotence describe pure states, and non-primitive, so formed by combining idempotence, then describe density matrices. And this was the idea for in 1930s to describe quantum mechanics without using the wave function. But I guess Basil will also add something and have to say something, and I'm done now. It was just
what you said is very interesting, because our local Nobel Prize here, Anton Zeilinger, told me that first was the word, that is discrete things. And as you said about the position between Schrödinger and von Jordan was discretization and continuous, and that's an interesting remark. Thank you.
You're welcome. Now.
Thank you. Basil, please go ahead.
Yeah, I wanted to take up the point about h bar going to 0. Now, the problem here is that if you look at the mathematical structure that I was talking about, where you had the star product as introduced in my lecture course, what you find there is that the Moyal bracket is divided by h bar. So if you put h bar equal to 0, the whole theory blows up. And I believe there was some work that Ernst Binz did, which showed that if you put h bar equal to 0 in the algebraic approach in general, you find that the theory actually it actually blows up. You get a singularity. You don't get to the classical limit. And I don't know how that fits in with what you're saying, Maurice.
No, one should never put h bar equal to 0 in quantum mechanics.
Yeah, but I'm trying to say the reason why I would not put it equal to 0 is because of these results with the Moyal algebras.
Thank you.
Yeah, but it might be related to what Michael talked about, the sub-Planckian scale also. If you put h bar equal to 0, some things disappear or are destroyed. I think the limit h bar equal to 0 is much more singular and worse than just some mathematical artifacts or things like that. And again, to say that h bar is small, we should ask small with respect to what?
Yeah.
Thank you.
Yeah, I can make a comment about that, if I may.
Yes, please.
Yes, you rightly said, Maurice, that the limit of h bar becoming small, the asymptotics of small h bar, as I prefer to call it, is highly singular. And this doesn't, of course, mean that you never will get classical mechanics. It means that you must introduce something else into the theory in order to get classical mechanics. And the simplest case is if you just have interference of two waves. As you make Planck's constant smaller and smaller, the interference persists, it oscillates, and eventually it will get so small that no practical experiment can resolve it. And then you smooth the observables, and then, of course, you get classical mechanics. And this it goes into many different areas. It goes right back to Thomas Young, who was criticized by people who said, why don't we see these interference oscillations everywhere? And he understood very clearly, and Fresnel in more mathematical detail, that it's because you eventually have a practical smoothing. You could call this a weak limit if you want to use mathematical terminology. And underlying this is something that Ian Percival emphasized, which is this. There's a difference between understanding the classical limit of the formalism of quantum mechanics, commutators become Poisson brackets and all of that, or commutators go to 0, etc., and understanding the asymptotics of the solutions of the formalism. And that's a much more practical, interesting concept, because we deal very often with cases that are almost classical, but not quite. And there's a huge literature on the degree to which one can and can't replace certain degrees of freedom by classical ones, and others you have to keep quantum, and so on. And this is pretty well understood now. It's understood that the limit is so singular that if you want the reassurance that something is classical, you need to do something else, which essentially involves smoothing out interference in generally understood. But a deeper question is this, and it only arises because the limit is singular. What properties are there which are semi-classical in the sense that they emerge only for small h bar, but are nevertheless quantum? And there are such properties. There wouldn't be any if the limit was smooth. There's an analogy. In statistical mechanics, the limit of large n is a singular limit in the sense that near a critical point, you never reach thermodynamics. Instead, you reach a critical state in which all of renormalization theory and so on is related to, and the universal features there, which arise for large n but which are not thermodynamic, are critical exponents and related matters. And there's a huge literature in physics of condensed matter. And this is a common feature in fluid mechanics. If you want to let the viscosity go to zero, you can't do that because in many cases, because you get turbulence, and it means that the dissipation goes to zero, but it gets distributed over a fractal set in the fluid. So there are many examples. I've emphasized this as a general principle where singular limits underlie theories that should be the limit to one another, but which are very different in their conceptual structure. And this is a contribution to what the philosophers talk about, which is the theory of emergence, but which they never understand because they don't realize that underlying it is the mathematical problem of singular limits, which is different in different areas of physics, but the common feature is this singular limit, and quantum to classical is one of them. So the question is, do you want the reassurance exercise of knowing eventually if h bar is small enough, you will observe classical behavior? You know the answer will be yes. It's difficult to show it, but it will be. Or the constructive, creative aspect, which is what new phenomena emerge as you approach the limit. And this is another area of intense activity. So, Maurice, you're quite right, just in this two words to say singular limit, but there's a great deal more behind it.
Do you think, Michael, that the notion of super oscillations could play some role there?
Well, I was going to ask the question about that because because the following. Basically, I think, you see, the uncertainty principle is, in whichever form you take it, is a rather crude thing. It deals with variances of wave functions. So it's blind to localized regions where you get very fast oscillations. So super oscillation can occur, and they don't contradict the uncertainty principle. But my question would have been, is there any semi-classical aspect of this related to the Gromov theorem? And I suspect the answer is no, because super oscillations are very deeply quantum things or very deeply wavy things. So in a sense, it's a different regime, but still, it would be wonderful if there were some reflection of the Gromov theorem that did not exclude super oscillations.
Don't you think that actually Gromov's theorem is an imprint of quantum mechanics in classical mechanics rather than the universe? Well, what do you think?
No. Good. It's a good question, and that underlies my question to you about the detailed behavior of quantum states when they evolve and become complicated.
Yeah. Thank you. Could I make a remark? Our present discussion makes an assumption that there are only two kinds of mechanics: quantum mechanics for small systems and classical mechanics for large systems. But let's look at the experimental status. If you, let's say, consider an object made of 10 to the power 9 or billion atoms, is neither too small, is not too large, and we have not in the laboratory tested quantum mechanics for such so-called mesoscopic systems. And perhaps it could be that it has an effective h bar which is smaller than h bar, and gradually proceeding to zero. Michael, I would like your response on this.
Sorry, this is not right. Mesoscopic quantum physics is a very large, experimentally flourishing area of condensed matter physics, and there isn't the slightest hint of any variation of Planck's constant or deviation from quantum mechanics.
I think,
as you discussed, it experiments in many areas of condensed matter physics are mesoscopic.
That is because you are not taking isolated systems. These systems are interacting with the environment. What I'm asking is try to do a double slit interference experiment with a particle made up of 1 billion atoms. Such experiments have not been done. That's how, this Girardi-Rimini-Weber theory of spontaneous collapse is still around, that as the quantum system becomes larger and larger, some stochasticity becomes more and more important to drive it to classicality and destroy superpositions.
Yes, you're right about that. But so far, the experiments have a few thousand particles. That's pretty surprising. And the way it works is these systems can actually be quite hot in experiments of in Zeilinger's group in Vienna. Right. They can be quite hot, but the degrees of freedom that cause the interference, which is the degrees of freedom not internal but center of mass degrees of freedom, don't share the high temperature. So of course it's very important to in testing ideas like Roger Penrose that maybe gravity would ultimately cause quantum mechanics to go wrong. So it's very important to do these tests for larger and larger systems. But my point was that so far, even when you have a few thousand particles, there's not the slightest hint.
I agree. I totally agree. But I make a claim that a few thousand is not large enough. It's very small compared to 10 to the 23. We have to go somewhere around 10 to the 10, 10 to the 11. And perhaps something is happening there.
Yeah, I mean, there are macroscopic quantum effects like superconductivity and so on.
Yes.
And of course, the fundamental aspects like the spin statistics connection, anti-symmetry of powers. I mean, this applies and has consequences for systems which are macroscopic, and these are also confirmed experimentally. So you're right. There may well be other. Look, I'll tell you something else. I mean, something I've been looking at, even in Newtonian mechanics, at the very first line of Maurice's paper assumes that the forces are derived from a potential. Now, when they're not, you can imagine forces which depend only on position, but which are not derived from potential, whose curl is not zero. Pragya Shukla and I, in the last 10 years, have written a number of papers. These have very unusual properties. And the question is it possible to quantize? This will be, as you just suggested, a different theory. We have ideas about that, but it's very difficult. So, and I remember when I met Stephen Weinberg many years ago, he was investigating if quantum mechanics were not linear.
Yes, I know.
What would you then determine? And he calculated that in some way of measuring, nonlinearity was excluded up to something like 10 to the minus 30.
For small systems, but not he. I don't know whether his result applies.
Yes, you're right.
For atoms.
Yes,
I'm very tempted to check if Roger is around. And would he like to take part in this discussion? I'd love to hear his views.
Yes. Well, and there's something else which I've recently emphasized. We like to think that quantum mechanics explains everything to do with matter. And then people say, well, in principle. Well, quite a lot of matter, which we exemplify by our mere presence, is alive. And we have no idea where aliveness is in quantum mechanics. Now, whether it involves some asymptotics that is very far from what we can achieve at the present time, or whether quantum somehow goes wrong, we don't know. But it's a point to bear in mind when we physicists like to say, we explain all of matter. Well, not aliveness.
Yeah, I agree. Roger, I have a question for you. If you could kindly unmute yourself
Me?
And asking Roger to unmute himself.
I must leave. Thank you very much, Maurice.
Thank you.
Thank you.
Can you hear me now?
Yeah, yes, Roger, we can hear you. I wanted to seek your views on the quantum to classical transition. Is quantum mechanics breaking down in the classical limit?
No.
Please go ahead.
My position certainly is when you bring gravity into the picture, then you have to consider that. I mean, the collapse of the wave function, according to my particular point of view, comes about when gravity becomes important. And so you have to, I mean, I had this argument quite a long time ago, which depends on looking at the principle of equivalence, which is, of course, the foundation of general relativity, and the principle of superposition. And I argued that there is a conflict between these two principles. No experiment as yet has got to the level where you would expect to see the collapse of the wave function coming about in a controlled way. I mean, it comes about in an uncontrolled way when the environment gets involved and you don't really know what's going on. But if you have a pure system where the environment is not involved, I mean, you can get it. Yes.
Yeah, thank you. So what you're saying is that as the quantum system becomes larger and larger, some things, say gravity, must come into play and in some sense modify quantum mechanics in a non-trivial way.
Yes. And also there's a sort of relationship between the length of time and the size. So a big system, the collapse would be very rapid, and for a small system, take much longer. And all the experiments, such as the ones referred to earlier, so far haven't reached this level. It'll be several years yet.
Yeah, I could also take this opportunity to say something about the correspondence Basil and you are having on whether there are two physical realities or only one. So I've been trying to understand how in the Heisenberg picture you don't have collapse. I was talking to Basil before the session started. One thing which we, I think, did not look at in that correspondence, Basil agreed that for him to get probabilities, he has randomness in the initial conditions with probabilities assigned to them. His evolution is deterministic, but he must reproduce what we see in quantum measurements, namely indeterministic outcomes. So for that, he would choose his initial condition randomly, like you said, what Bohm was trying to do. So I think to make Basil's Heisenberg picture consistent with your picture, it seems to me he will have to have a random probability distribution in his initial conditions. Basil, are you there?
Yes, I'm here. Yeah, no, I make that assumption. The idea is that you start with a system in which the position of momentum are well defined, but you cannot produce a system with an a priori given well-defined Q and P. In other words, it's the way you set it up that introduces the probability aspects. But it doesn't mean that the development is not, if you like, I wouldn't like to use the word causal, I don't like to use the word deterministic, but follows the set of algebraic rules, which I tried to set up in my talk. And in fact, they're not my rules, they're rules that are well known in other areas of physics. And it just seemed to me that they were the way of getting over this difficulty of a collapse, because
Yeah,
when
but
you look at the final probability, what you're doing essentially is you're dealing with reducible representations for your time development. But when you face an experimental situation, you must look at the irreducible representations.
But my understanding is that by putting the randomness in the initial conditions instead of in the collapse, you have done it differently from Roger, but I no longer see any contradiction between his stance and yours.
No, but I only get one reality, whereas Roger seems to get two.
No,
And,
but I think, Basil, I think your second reality is in your random initial conditions.
I mean, the two realities come about only because you have collapse. And if you
see,
I don't understand the point of view that Basil was describing, in which he seems to get away from having to have collapse, and I don't understand that.
That's right, and I don't understand why you don't understand what I'm saying, Roger.
Well, do you have collapse in your picture?
No, I don't have a collapse.
But
look, let's go right back to the simple bone mechanics, Bohmian mechanics, if you like. I don't like that because it doesn't answer. It answers some questions, but leaves a lot to be desired. But what that does, it starts with the Schrödinger equation, simply polar decomposes the wave function, and we get two equations resulting from that when we take the real and imaginary parts. One gives you the conservation of probability, the other one gives you the conservation of energy, from which you can obtain the Hamiltonian flows that Maurice was talking about. And in the Hamiltonian flows, the system just evolves. The final probability distribution is such that when you integrate over all the final solutions of those equations, you find that you get the probability distribution that quantum mechanics gives you. That's why I'm saying that my collapse is not, I'm not giving the wave function an ontology as such.
That's very close to what we call Bohmian mechanics, yeah?
Sorry?
Bohm would put the probabilities in the initial conditions.
That's where I'm getting, because I worked a lot on the original Bohm model. I had a whole host of research students who worked just to see what the things looked like. Not necessarily saying nature was like this, but here we had some very simple mathematics which showed that you could get, as Maurice put, some Hamiltonian flows out. Do the particles flow along those lines? I don't know. But what I do know is that energy flows along those lines. And what you find is that in order to make this consistent, it comes out of the Schrödinger equation. You don't have to put anything in. There is this extra energy which we call the quantum potential energy. And it's the energy that Maurice talked about when he was talking about the Green's functions, the classical Green's functions, as opposed to the quantum Green's functions. And it's from the Green's function approach in the book he advertised, the one I wrote a forward to, and that one actually shows that if you add this extra h bar squared q to the propagator, you get the Schrödinger equation. I mean, that was the whole point about what he was saying, and he's got a much better way of justifying that now. So in that story, there is no collapse. Now, you might say that story is wrong. That's fine. That's good. Then we know where we are. And I'm not saying that the Schrödinger picture is wrong. I'm saying we're using an algorithm which is not reflecting correctly what is actually taking place in reality. I know that word reality is a very difficult, slippery customer. And that's why I'm reaching my position. That doesn't mean to say that gravity might not come in and change the flows. That's what I'm hoping would happen.
But I still don't understand how you can avoid collapse. I mean, you're saying that the Heisenberg picture somehow gets around it. I don't understand. I mean,
what about the simple picture that Bohm published in the 1952 paper, where he takes the Schrödinger equation, writes the wave function in its real and imaginary parts, looks at the Schrödinger equation in terms of the real and imaginary parts, separate them out, and you find the real part gives you these Hamiltonian flows, which tell you what points on the screen correspond to the initial condition. And you integrate over the final conditions and you get the quantum probability out, given the initial contribution, as Tajinder was saying just now, the initial probability distribution.
Roger, my understanding was that the randomness which arises in what we call collapse of the wave function, they have removed it from there. Their evolution is deterministic through and through, but the initial conditions are chosen randomly so that repeated deterministic evolutions lead to different outcomes consistent with the Born probability rule because the initial conditions are so chosen.
Thank you, Tajinder. That's exactly what I should have said.
Thank you. Thank you. Roger, does that at least in principle explain what their viewpoint is?
Not enough to me, I'm afraid.
Okay.
I mean, the idea, I take it the argument is that you have these parameters in the initial state which are uncontrollable, and that the collapse effectively comes about because you haven't, I mean, these parameters determine the way the thing collapses, but they haven't been put into your initial state.
Yes.
Like that.
But yeah, my parameters are just position and momentum. My parameters are just position and momentum. I haven't introduced any. I mean, one of the tragedies of the Bohm 52 paper was the title he chose, which was hidden variables. So that immediately stirs a wasp's nest of arguments that went on in the 1935 era. Is quantum mechanics complete, where Einstein and Bohr had those extensive debates. There are no, as far as I can see, there are no hidden parameters in the Bohm theory at all. You can say, oh, but what physical reason are you giving your X and P? Then you could say, well, the point of them being hidden is that you cannot actually, it's not that they're hidden, it's just that you cannot prepare a state in which a priori you can choose a given P and a given Q. But that's an experimental feature. Now you might like to understand what that means. Fair enough.
Yeah, I was thinking that suppose we asked, is there an experiment which tells us whether the randomness is in the initial conditions or in the interaction of the quantum system with the measuring apparatus? I think we don't have an experiment which can tell these two interpretations apart, to my understanding.
I think I'm sorry, that's what I think you're right.
My own inclination is for the collapse, but I cannot disprove experimentally your proposal.
No, but the problem with the collapse is it's been around for 100 years. And a lot of very clever people, far cleverer than me, have not solved the problem. And
Yeah.
Roger's trying to solve the problem, and I take my hat off to you, Roger. Please, I'm not saying don't carry on, for goodness sake. What I'm saying is I just feel this other way that I've been looking at it offers more in the way of avoiding this problem, if you like, and producing one reality.
Yeah, but look at it this way, Basil. Here's a new proposal. Allow for the Hamiltonian to have an anti-self-adjoint part so that your evolution for microscopic systems is unitary. But the anti-self-adjoint part starts to become more important for large systems. The evolution now is deterministic but not unitary. Deterministic, not unitary, and I can say norm preserving. Here, I think we can get something like breakdown of superposition. And if you are coarse graining, not observing at a very fine grain level, then you coarse grain, you probably will get randomness in the spirit of Brownian motion. So this is perhaps, and you are saying the problem has not been solved for 100 years, is true, but we are trying. So,
yeah, but are you taking me back to the Vienna approach?
In a subtle, nuanced way, because the evolution is deterministic but non-unitary.
Okay, but what Vienna had to do was to introduce two Brownian motions. And I never understood why he introduced two Brownian motions, except perhaps for saying that there was a position representation needed one Brownian motion, the momentum needed another Brownian, and you better make sure that the two Brownian motions are coherent with each other so that you will get the what you expect from the Fourier transform from one representation to the other.
Yeah, so no, not this. The Brownian motion arises only after coarse graining because we are not observing the quantum system at the deeper level where the evolution is deterministic and non-unitary. If you like, maybe this is happening at the Planck length scale, but if you observe at a at a larger length scale where you have a poorer resolution, then it would start to appear that the outcomes are random, whereas they're not random, but there is a breakdown of superposition because of non-unitarity. So Steve Adler.
Yeah, but you see, superposition is already assuming that the dynamics is giving you a superposition of states.
Yeah, so I'm saying that is true, strongly true for small systems, but gets more and more weakly true as the system becomes large. Fundamental evolution is non-unitary. I don't put non-unitarity in just at the time of collapse. I put it in the dynamics. So my Hamiltonian is not self-adjoint. You could put it that way.
Mm-hmm.
Look, I mean, fine.
No, I'm saying
I'm not stopping you. I don't know how to do it. Sorry.
Yeah, we are trying. I mean, just because 100 years have passed should not be a reason to say that it cannot be done.
I think you need some new idea.
Yeah. I think I like Steve Adler's trace dynamics a lot. It's a deterministic, non-unitary evolution, but unfortunately, trace dynamics has not become popular.
I'm sorry, I know nothing about it, so I'm in your hands.
Thank you. Roger, anything more?
No, there are lots of things I don't understand. And
oh, please, Roger. There's thousands of things I don't understand, far more than you don't understand.
Yeah, but I really enjoyed your email correspondence, which I was fortunate enough to be CC'd into. I read all the mails quite carefully, and I was trying
another one which I haven't finished yet. But
No, I haven't given you enough time to reply, you see.
Okay.
No, it's just, I'm sorry, I've been very tied up with getting my eyes sorted out.
Oh dear, mine aren't sorted out.
I know, that's why I don't complain in front of you, Roger, because mine can be sorted out.
Yeah,
So
okay.
they reassure me.
We'll probably go to the next question, sir, if you don't mind.
Sorry.
Christy, please unmute you. Sorry to make you wait so long, Christy.
I enjoyed the discussion, but I have a question about the talk, more direct, I hope. It's so when you show this correspondence between quantum blobs and Heisenberg's, I mean the Robertson-Schrödinger uncertainty principle. So this involves two observables that don't commute. This poses some limitations. You cannot measure the two observables simultaneously and get an accurate result. But there is another limitation to quantum measurements, which is given by the Wigner-Araki-Yanase theorem, which is apparently only about the observable that you measure. It is obstructed by conservation law. For example, in Wigner's paper, which started this chain of theorems, in fact, because there are more theorems, he discussed the measurement of the spin along an axis and the conservation of the spin of the angular momentum along an orthogonal axis obstructs the possibility to get an accurate measurement which leaves the state unchanged, so that you can repeat the measurement. So my question is whether there is something in the symplectic geometry of the phase space that can explain or in the same way quantum blobs explain in a different way the uncertainty principle. I mean, the uncertainty principle is understood in various ways. For example, by the properties of the Fourier transform, or by properties of the operators that don't commute. And one of them, which I enjoy very much, is the geometric one that you provided. And I'm interested if it's possible to do the same for a single observable when you measure it due to the Wigner-Araki-Yanase theorem.
I don't know. Actually, because you see, I think that Michael Berry went to the point there must be a richer structure under all that. I don't think that the Wigner formalism alone allows you to explain these things there. I mean, we need something finer, but I don't know what. And I wasn't aware of what you told me actually about the spin thing. So just perhaps just a lack of knowledge. So I'm sorry for that to give that answer.
Yes, the theorem applies to any observable basically, because any observable, as long as you find an additive observable that is conserved during the measurement, so that you can use the conservation for the combination of the apparatus and the particle.
Okay, so you add the conservation law in effect.
So yeah, it depends on the dynamics, of course, because you need to measure the interaction between the apparatus and the observed particle. But this, the conservation laws, if they happen to be in a particular relation, which usually happens, you cannot have a measurement of that observable, which is both accurate, so that if the observed system is in an angular state already, you get the right eigenvalue from the measurement, and also is not disturbed so that you cannot repeat the measurement. And the simple example is with spin, because it's the most used example. So it's very simple, and you already have 3 directions, so you can find, and it's conserved. So, I mean, the angular momentum is conserved. So you can find a way to choose the conserved and additive quantity that that doesn't commute with the one that you observe. So it's easy and natural, but it also works for different observables, and it allows, for example, to show that you cannot get an accurate and repeatable measurement of an observable that has a continuous spectrum. So unless you are happy with the discrete result, for example, it's on the left or on the or on the right, or something like this. And somehow by reading a lot of literature about this, I have the feeling that it is in the Platonic world related to the uncertainty principle, but I cannot put my finger yet to show how. And I hoped that quantum blobs may give an answer. But of course, if you didn't think about this...
no, but yeah. Christy, I think we know where to find each other on internet. So perhaps you could send me, please send me some things you have written about that, because I would be interested in reading that.
Yeah, absolutely. Okay.
Okay.
Yes. Thank you very much.
Thank you. Any more questions, please? Last thing, Bernd, would you like to say your comment?
Yes, of course. Actually, so there's something which I learned by reading Born and Jordan and other authors. So what we normally assume in quantum mechanics is that time is a classical parameter. So a real number parameter. This means that every moment in time is predetermined. We have always, with a certainty of 1, we can, well, determine moments of time, and also the moment when we are doing a measurement. So this is one of the reasons why things are still, in a sense, deterministic in quantum mechanics. And of course, if you use a real time parameter, you also have a continuous and smooth evolution, and you probably shouldn't have any kind real jumps, so to speak, and also no wave function colors, because otherwise you would disturb the smooth evolution, which is based on this real time parameter, this classical time parameter. And I think it was in 1930, Jordan and Born, in a textbook on quantum mechanics, proposed to also give time quantum properties, so that it would be not possible to determine observables at a specific moment of time, because you could still measure time with arbitrary precision if you use self-adjoint operator, but then you would no longer be able to measure an observable which does not commute with the time operator. Or you can measure the observable, but then the time would be totally uncertain. And so this was an idea how to break out of this. We have a smooth and deterministic evolution, but we actually see quantum jumps, or we don't see macroscopic superpositions. And of course, at the same time, Pauli then proved that it is not possible in quantum mechanics to have a time operator, because then your Hamiltonian would not be bounded from below.
Pauli's proof is limited. There are ways to overcome it. Yeah, you know.
Yeah, but so yeah, of course you're right. But it was in 1930, so at that time people didn't know how to get around Pauli's theorem. That this was one of the how do you call it, historic branching points, where maybe things moved in the wrong direction, because everybody thought we need a classical time parameter. And in quantum field theory, we even have classical position and time parameters again. So this could be one of the reasons. Yeah.
In my view, there must exist a reformulation of quantum theory, even at low energies, in which space and time are not classical. I think that is very important. It's the gateway to quantum gravity, because to have classical space and classical time, you need classical bodies. That means you're already making quantum mechanics depend on its own limit. and that is not the best formulation of the theory.
This is actually what Bohr did. He said we always need classical measurement devices and a classical reality to make sense of the quantum reality and to get access to quantum reality. But I mean, this is one of the basic foundations of the Copenhagen interpretation. If you follow Bohr with that, we
need to go past that, right?
Yeah, maybe we need. So, as I said, I'm just making historical comments on how things turned out the way they are today, not how they are going to be or should be. So.
Maurice, could you kindly stop sharing so that we have the full screen? We can see each other and say bye.
But what should I? Okay.
Stop sharing.
Okay. I closed the PDF.
Yeah, great. So we all are together on the full screen. So if there are no more questions, we could please wind up the session. I just wanted to remind you that we are meeting after 1 week on 29th March. Christy, you have something to say?
He's just waving. This is the symbol for waving the hand.
So 29th of March, we have another very interesting lecture by Xavier Hernandez reporting the breakdown of Newton's law of gravitation in wide binary stellar systems. This is very important right now because if Newton gravitation is breaking down in these wide binaries, then dark matter cannot be an explanation. So it might be a blow to dark matter. 2 or 3 different groups are reporting that we have a breakdown of Newton on these very large radius stellar systems, about 2,000 kilo astronomical units. So hope to see you there next week. And thanks so much, Maurice, for a very beautiful lecture. I learned many new things. Thanks, Basil, for bringing Maurice to us and telling us about the symplectic camel. Beautiful theorem, no doubt. And your own work with the quantum blob. So
thank you very much.
Thank you, everyone. I'll log out now. Bye-bye.
Thank you, Maurice.
Thank you very much.
Bye, everybody.